things get tricky here. We're going to find the volume of the solid bounded by the graph of f of y. Oh no, okay. This is not a function of x, meaning it passes the vertical line test. It's a function of y, meaning it passes the horizontal line test. It might look like a function this way. It is not a function this way, but we are considering it like this. So for any input of y, I get an output of x. A little backwards of thinking about it. Don't panic. I do want to point out the way it looks, though, and the way it's graphed. You've seen this in a previous lesson, but just here goes. This is a parabola that is a y-squared parabola, so it is not an up-down parabola. It is a left-right parabola, and it is opening in a negative direction, so it opens to the left with a shift of 3, so 1, 2, 3, that pushes it forward. Okay, just good to know. And then 1/2 y. This slope is the slope of this line is 1/2, and I know that doesn't look like rise over run. It's actually run over rise. It's weird because this is backwards. So the cross sections, which are perpendicular to the y-axis now. Okay, so in the previous lesson, or previous video, you saw little like semicircles coming up or rectangles coming up, and they were coming up in a way that was like if I held my paper like this, it would be coming up like that. Where if I sliced it perpendicular to the x-axis, I would say, oh, look at that semicircle or triangle, whatever. Now I'm going to be slicing them this way. Okay, take a knife, you slice it this way. Cross sections are perpendicular to the y-axis, and they are squares. What I like to do, and you've seen this on the previous side of the notes, I like to write down the formula for what I'm dealing with. The length of a square, the area of a square, I should say, is the length of the side squared. The area of a semicircle is, well, pi r squared, but it's half a circle, so it's pi over 2 r squared. Okay, a rectangle, I'm just going to go ahead and go through and make all of them. A rectangle with a height that is 3 more than twice the base. Okay, whoa, what? Okay, a rectangle is base times height. And I may not know the base, but I do know the height is 3 more than 2 times that base. So 3 more than 2 times that base. And then rectangles with a height given by this. Like, whoa, what? Okay, well, I may not know the base, but I know the height. Again, it's BH, but it's B times H. And it gets this funky little thing going in here where you're going to have the base times that. Now, as we go through this, you might be like, well, what is the base? The base is this distance. So for our squares, you have a square that comes up out of the paper like that. Okay? You're not looking at it from the same perspective that I am. It comes up out of the paper like that. Or in this case, the base is this, and the height depends on the x value. I might modify that one in a minute and make it look like the y value instead, because these are functions of y. So I might tweak that problem. It's the first time I've done this problem. I've redone things. Isosceles right triangles with one leg in the coordinate plane. We dealt with this on the other side of the notes. But if I have an isosceles right triangle, one leg is in the coordinate plane, we basically have this situation. And it's like that. So if this is base, this is also base, so it would be 1/2 base squared. And then isosceles right triangles with a hypotenuse on the coordinate plane. I'd have this situation, that's B, there we go. And this would be, just we've been through it before, but this would be square root of B times 2. So, sorry, square root of 2 times B. Call it B times, we'll do it like that. And then we'll erase that random little mark right there. And then in the process of doing that, I would have, oh goodness, I gotta get my height as well. Sorry, I'm thinking through this process again. And so half of this would be that. So it would be 1/2 base. No, I'm messing this one up. I'm gonna get it right. Hold up. We did it a minute ago. Whatever the base is, we'll call this the base. This is the height. I don't need to call these the bases. They're not sitting in the coordinate plane. I think No mistakes, only happy accidents. Can't pretend like I do everything right the first time. The base is this. The legs of it are coming up like that, kind of three-dimensionally. They're coming up. And I need the height of this. So this length right here, we put it in red. This length right here is going to be, well, half the base. So half the base. I was going to finish that sentence, but that was the sentence. It's half the base. 1/2 base. So 1/2 base times 1/2 base, that'd be 1/4 base squared. Okay, we've made a list of all the formulas. That's what I like to do first. And so we will boink, go back to the top, and we're gonna find the area, I lied, find the volume, which is an accumulation of area. So here we go. Let's use green. As we do this, we're going along the y-axis. So all of these are going to be from this point of intersection to this point of intersection, but the y values. So it's going to be the integral from -2 to 1/2 of something dy. Okay? Well, the area of a square is b squared. How long is this? And you could be like, oh, that's 3. Okay, I hear you. But how long is this? And how long is this? And how long is this and this and this and this? For any given length I'm drawing, how do we find it? We would do the greater one, the rightmost one, minus the smaller one, the leftmost one. And the right one, not necessarily the correct one, is this. The leftmost one is that, and we must square it. Okay, I am really not interested in actually finding the volume. If you can set it up, you're good. At this point, it's a practice of typing things in the calculator. Okay, semicircles. Let's do this. Semicircles would be pi over 2. I like to put my constants in the front. You don't have to, but -2 to 1.5. And I need to know the radius. If this was a semicircle, if this was the diameter of a semicircle, because it comes up over, see, three-dimensionally, here we go. It's gonna come up over like that. And if that was the diameter, then the radius would be half of that. This distance, for any given distance, is big minus little, which is f minus g. So it's gonna be f minus g. I'm actually going to start calling it f of y minus g of y. I totally could have done that here. But it's divided by 2, and it is squared, and then dy. Now, if you're like, whoa, where'd all that come from? Again, the distance is the diameter. That's f minus g. I don't want the diameter. I want the radius, so we cut it in half. All right, let's keep going. The integral from -2 to 1.5. The thing that just went through my head was this. My eyes glanced over here. Do I have a constant in the front? No, then don't. Base. What is the base? It's f minus g. And then 3 plus 2b. All right, 3 plus 2. Oh, base. What's the base? It's f minus g. We get carried away with parentheses here. I've closed that one and that one and that one. Dy. Again, not interested in actually finding the volume. Love to. But what we're doing is accumulating area. I just feel like it's worth saying again. This is area. This is the accumulation of area, which gives me volume. Just as, I'm getting carried away, I'm having so much fun I can't stand it. Just as the area under a curve was an accumulation of all these infinite number of distances. You accumulate a lot of distances and you get area. You accumulate a lot of area and you get volume. You accumulate a lot of volume and you get whatever 4 dimensions is. I don't even know. All right, rectangles with a height given by this. I think we should modify this. And when I made the problem, my mind was in a different place. Just thinking of, like, how can I make this a spicy problem? And then I didn't realize it didn't jive with what I had because these should be y's, so the original problem should be y. I apologize. If I was truly considerate, I would make a whole new video just because of that mistake. Later versions of this will have it corrected. If you're like, wait, that's not on my paper, just go with it. So there we go. -2 to 1.5. And b All right, well, what's the base? F of, whoa, wrong color. It's supposed to be green. Oh, well. Now I have to start the video over. F of y, no, I'm not. Minus g of y times all the stuff. Well, what is that stuff? No, there is no what is that stuff. It's the stuff. It's y times the square root of 6 plus y. Well, do I need to solve for it? No, you don't. You don't. I changed that problem when I switched those to y's because I made the notes. I can change them if I want to. All right, let's use the correct color this time. Years from now, I'm going to be digging out these old notes and be like, man, why was that one purple? I should have made that video all over again. Why is that whited out? Integral from -2 to 1.5 of base squared. There's a constant. And my base is f minus g dy. That's it. Again, not interested in actually finding it. Whoa. Squared. All right, now we can get in a habit of being like, well, you're squared, so why aren't you squared? And why aren't you squared? No, yes. Whatever you have as your area, that's what goes here. And if it ain't squared, don't square it. Okay, last one. The area, accumulation of areas, from -2 to 1.5, and it's 1/4 base squared. So this is the same problem as the last one, only we have a 1/4 in the front, f of y minus g of y. And we're squaring the entire difference, not just squaring them individually, which is different than something we're going to do later on.